very good morning to all of you. In the last class, we learnt about the various kinds of faults which can occur in an VLSI chip. Essentially, during fabrication, there will be defects. Those defects could be a cut in the wire connection, or it could be an unnecessary connection between two wires. Or there could be a transistor which is not fabricated properly. So VTH may be way too high, or it could be way too low. So those are the defects, but it is difficult to model all those defects. So we learned that it's a better option would be to model all those defects as faults, and faults is nothing but there are certain kinds of faults like stuck at 0, stuck at 1. That means any net is stuck at 0 means it's permanently at 0, or it's permanently at 1, irrespective of what is actually supposed to be there. And then we talked about delay faults, we talked about transistor faults, and there were 3 or 4 kinds of faults which we discussed, right? So now let's try and think what is testability from on an upper, how to go about doing testing. So first and foremost thing is to make an list of faults, right, in a circuit. So given a circuit, so I should run an algorithm and try to list down the faults. Okay, so the first step is going to be to make an list of faults. Okay, once this I am giving an overview, and over the next 6 lectures we will see each component. Okay, so right now we have just made a list of what could be the faults that we learnt in the last class. Now this list, right, okay, this could be very large. Now I can do something known as fault collapsing, because there could be, I don't know, this pointer. Okay, there is a list of faults, and from these faults I am going to I am doing some faults collapsing. That means some of those faults, if you check say one particular fault, simultaneously there is a possibility that other fault is also getting detected, right? Suppose I have an AND gate, I am checking for this fault. Okay, even this, there is some fault here is also getting checked because of that particular test vector. Okay, I am not really interested if it has gotten this fault or this fault. As long as this is faulty, this gate is faulty, right? So if I do this is known as fault collapsing, which we are going to learn today, so that the list becomes small. If this is a trimmed list, then obviously that much lesser time would be taken for doing the testing, right? So we do the fault collapsing. Now after doing the fault collapsing, right, generally what we do is these faults we categorize into 2. Some are difficult to detect and some are easy to detect. Okay, so we are going to run some algorithm which will classify these faults into 2 categories. Okay, now some are easy to detect. Now these easy to detect, okay, faults, we are not going to take one each fault and try to run a test vector, try to find a test vector for that. What we are going to do is, right, what are the most of the algorithms, how do they work is, we will try to apply, the algorithm will try to apply a random test pattern. Okay, and for this one particular test pattern, it will tick, okay, what are the faults which are covered already, which are covered, right? Then it will take the next random pattern, then the next random pattern. So it will generate a list of random patterns and try to cover all the faults which are easy to detect. Okay, and then for the remaining which are difficult to detect, okay, we will take one each of them. Then now you have to do that customized run, right? Because for that particular fault, you try and find what is the test vector required. So this is all about testing. So finally, what should be the output? There is a fault list, and then there has to be an test vector for each of these faults, right? And there has to be a matrix which gives me the correct results. Alright, what is the correct expected result? If I give 0, 0, 0, the correct one is say 1, 1, 1, and then the that this metric should be available to me, right? Only then I can detect these faults. And if it is not, then what are the gates which are faulty? So this is the final thing which I want. Is it understood? What I do? If I repeat, first I have all the faults, right? All the faults which can happen in a circuit. So I'll run some software, some program which will pick up all the faults in the circuit. Okay, once that is done, I have to optimize. There is no point. We will learn today that so many faults can be detected by a single test vector. So you need to collapse the faults and minimize the list. Once that is minimized, then I classify these faults into two categories. One, those are difficult, and one, those are easy. Okay, so this also we will learn. At each of these there are several algorithms. This is what throughout the course we will be learning. And then we have all the easy ones which are detected. We then we don't handle after detecting what is easy. We are not going to handle each fault and try to create a test vector for that. What we are going to create a random test pattern, and for each random we'll keep ticking. Okay, one particular random test pattern has been given from this easy list. How many have been killed in one go? Maybe 3 fault has got killed, has been detected, or 5 has been detected. So we just keep removing that from the list. Then we go to the next pattern. Okay, similarly we will keep. It is not done in a sequential manner. That also we will discuss why random test. What's the advantage here? So we'll keep doing random test patterns and cover all the faults out here. Okay, once that is done, few will be remaining, and those few, for those few, if you start doing the random test pattern, it will take a lot of time, and you may not come across those faults at all. So what we do is, then we take those limited number of faults, each one of them we will handle as a single fault and try to find what is the test vector to detect that fault. So so overall, how to go about designing a test bench, is it okay? Some rough idea you have got? Okay. Right. So this we saw functional testing versus structural testing. Like we discussed last time, that if I have a 64 bit into 64 bit plus a carry in also which is coming, so it becomes a 120 64 plus the carry in 129. Different combinations are possible. So if you try to do an calculation of that and try to give each combination and try to see if the output is same, then we might take at 1 gigahertz and a frequency, because these many test vectors are required, 2 to the power of 129, and if 1 gigahertz is the frequency which we employ for testing, then it would take 22 years. Okay, just for this one. So if you can consider if there is an even this is not physically possible, right? So you can just imagine for a microprocessor what is going to be the state of affairs, right?
So how this number 6.8 came? 6.8?
No, 2 to the power of 129.
Okay, then how we decided 6.8?
No, this I have written in decimals, just in
Okay.
calculator. If I put 2 to the power of 129, it would come like this, right?
Okay.
2 to the power of 2 is 4, right? Like that.
We converted in 10 to the power only.
Yeah,
Okay,
that's
fine.
Then we said instead of doing that, what we can do is, this is a full adder, right? This is how a carry looks like. No, a sum looks like. There are two. These are the faults which can stuck at 0, stuck at 1, stuck at 0, stuck at 1. So there are 1, 2, 3, 4, 5 nets, right? So there are 10 faults in this circuit. Right? Similarly, if I go for the carry circuit, then there are 17 faults. So 10 plus 17 is 27, and I have 64 such adders. So 64 into 10 plus 17. So only those many test vectors are required. So you find this would come out to maybe what 1000, say less than 2000, some figure like that. But even in that, also this is much lesser will be there, because we are going to learn about fault collapsing today. So it makes sense to do structural testing, right? But functional verification, we say, like I explained in the very first class, there is some bit of functional testing required in the critical parts, and also small module by module you can do functional test, and when you assemble those modules into a bigger module, some critical path testing has to be done. Okay, only then we need not do 100% testing. That is what we learned in the formal test verification part, right? Okay. Now coming back to
Sir,
yeah,
could you please go to last slide?
yeah.
In the right-hand circuit down, so points which are near to AND gates, SA1, SA1. So why we are considering only like stuck at 1, and at output where we are considering only stuck at 0?
Here.
Yeah.
Okay. Okay. This is an collapsed one. So I'll just explain you why we are doing that. Okay.
Okay.
Okay. I'll explain that. Okay. Now single stuck at faults. So how many fault sites are there? 1, 2, 3. Right. So there are 3 faults. So how many faults are there? So at each of these faults, it could be stuck at 0 or stuck at 1. So there are 6 faults. So minimum actually, if I write, if I make this table, okay. So how this table is made is very important to, because throughout this lecture we will be referring to such tables. Okay. So let's just recall what this table is. 0, 0 is the test vector. This is fault free output. So 0, 0, 1. 0, 1 is 0. For 1, 1 I have 1, and for 1, 0 I have 0 here, right? So this is the test vectors, 4 test vectors, and these are the fault free operations. Okay, all. Now if A is stuck at 0, this will be 0. Okay, this will be 0. For this combination it will be 0. So where it is marked red, okay, that means there is a variation from the fault free operation, and hence 1, 1 test vector will give me whether A0 can be detected. If A is stuck at 0, if I have to find out, then what is the test vector needs to be given? 1, 1. Okay, so this red indicates that. And similarly, if A is stuck at 1, even if I give 0, 1, since A is stuck at 1, I will get 1. So this red indicates it is different from the fault free output. Okay, only then we can detect the faults, right? So from this table, if you see here, this C stuck at 1 can also be detected by this test vector. I am giving 0, 1, right? If A is stuck at 1, I will get 1, and if C is stuck at 1 also, I will get 1. So really it doesn't make any sense to give these 2 test vectors. If A is stuck at 1 and C is stuck at, my aim is to just to verify if there is any fault in the gate. Okay, whether fault is here, I cannot use it in my application, right? So I'll discard it. So there is I need not tell. Right, although the fabrication engineer might be interested in finding out what which is the one, so that he can take the necessary corrective action, right? But as far as the testing is concerned, here I am just interested in the functioning of the gate. Okay, once I tell this gate is bad, the fab engineer might want to further do these 2 tests separately and try to find out where exactly is the fault, and probably institute corrective measures. Okay, that is later on. But at the preliminary test level, from a pure test engineer point of view, I just have to pass this gate or fail this gate. So only 3 test vectors are required here. Okay, so yeah, is this table okay with all of you?
Yes, sir.
Okay. Okay. Now we also saw we need there is something known as delay faults. So there are different paths in this circuit. This from the last class only. So there are several paths, and they could be slow to rise or slow to rise and slow to fall faults. And for those kind of test vectors, you need to give to find out those kind of faults, you need to give 2 set of test vectors. Okay, one test vector to create one state, and the other test vector to create the other state, and these combination of these test vectors will make a transition, right? So that transition can be observed, and you can say whether it is rising, it is rising within the given limits, okay, the rise time and the fall time, whether they are in the within the limits or not. Okay, so for all delay faults, two types of test vectors are required. Okay, just a quick recap of what we learned in the last class. Okay, then we also learned about transistor faults. So there could be two types of transistor faults. One is transistor getting fabricated in the open condition. That means even if you give the gate signal, this remains open, right? So all these open transistor faults also requires two kinds of test vectors. Okay, this also I explained to you in the last class, that there will be like this test vector followed by this test vector. Okay, these two test vectors will only give me what is the fault, right? Otherwise a single test vector may not will not be able to identify open transistor fault. So two. So this also we saw in the last class. Okay, now coming to today's class, see what is fault detection is, if I give a test vector, okay, the actual thing without a fault and with a fault, they should be a complement, right? Only that. Suppose I have a stuck at fault 1 out here. Okay, now if I have to identify that, so that test vector should be, and here I have to be, sorry, I have to give 1, I have to give 0. If I have to find stuck at 0, first I have to activate a 0 in this line, and I say that, okay, it is, the output is 0 in case there is no fault, and I say output is 1 if there is a fault. So they are, you see, they are complementary. So this is known as a fault and a fault free output, and this is known as with fault, okay, output. So this condition, so this can be anything, okay, doesn't matter, because we are talking about this particular fault. So our aim is to identify. So we need to, for each of the faults in the circuit, two things have to be identified. One is the test vector, and even the correct result and the faulty result. So both this information are required for the test bench to run automatically, right? That corresponding test vector as well as the faulty output and the correct output and the faulty output. So both this information are required finally to develop an test bench, right? Now there are actually three different steps, okay, when I talk about fault detection. Okay, the first is fault sensitization. Okay, now suppose this is stuck at 1. Okay, this is the fault which I want to identify. So the first step is, if it is stuck at 1, then I need to create a 0 here. Okay, that is known as fault sensitization. What is fault sensitization? If it is stuck at 1, then I need to push a 0 here. Okay, so that first part of selecting a fault and providing a complementary output at that particular node is known as fault sensitization. In this example, if I have to find stuck at 1, then I will give x3 is equal to 1. So that 1 will give me 0 here. Okay, so now I am complementary stuck. I'm trying to find out a stuck at. If I have to find a stuck at 0 fault here, if I have to identify, then I give stuck at 0, then I give, no, suppose I have to give, yeah, stuck at 0, then I have to put a 1 here, then I will give x is equal to 0. In this particular case, I am trying to find out stuck at 1 fault. Okay, so I have to force a 0 here. So how to force a 0? I give a 1 here. Okay, so this is the first step, which is known as a fault sensitization. Okay, once we do the sensitization, next is to choose fault propagation. So we just choose a path. Okay, now in this particular case, in this particular circuit, there is a single path. Okay, so I identify G4 and G5 are the gates through which I will do the propagation of the fault. Like later on we will see algorithms, there will be multiple paths, and how to choose an appropriate path, we will see that, okay, later on in the next class or next to next class. As of now, I am just covering the definition of what is fault propagation. Okay, so fault propagation is nothing but after having activated the fault site, okay, with a complementary signal which is known as sensitization, I identify the gates through which the output, because finally this is only observable point. Okay, these points are not observable points. Okay, only here I can see the output, so I need to get this fault here. So this is known as fault propagation. And the third one is fault justification. What is justification is, now for this fault to appear here, this gate needs to be justified. That means I need to give a 1 here, because if I give a 0 here, this will be permanently 0. So I need to give a 1 here, right? If I have to give a 1 here, okay, now this gate also has to pass, right, has to provide me 1 here. I am already giving 1 here, so I have to give 1 here, right? And if there is a 1 here, I can probably choose a 1 and 0 here, right? And similarly, this G4 gate has to propagate this here, so I need to give 1 here, right? So a fault justification is nothing but once you have found the path till output, now working backwards, I try to assign the inputs. Okay, so these are the 3 distinct steps involved in locating the faults and finding the test corresponding test vectors for every fault. Okay, so these are the 3 important steps involved. Before I take on anything new, let me just cover this particular aspect also, that faults detectability. Okay, certain faults may not be able to we may not be able to detect. Okay, like in this case, this is a like I discussed in detail in the last class, there could be a redundant gate out here, right? So this is just to avoid hazard. Okay, hazard is unnecessary transition, right? So once you have a redundant gate which a designer has put for meeting his timing requirements and reduce hazard, for the test engineer this becomes a nightmare, and he will not be able to detect this fault here. So all faults may not be may not be able to detect. Okay, so that should be known, otherwise we will spend time and effort and trying to identify these faults. Okay, so you can say the other way around. If some fault is not being detected, okay, when we are running our algorithms and we find that this fault cannot be detected, it means there is a redundancy in the circuit. Okay, so if unintentionally some redundancy has come into the circuit, then the test engineer can point out, okay, this fault is not being detected, so probably there is some redundancy in the circuit, so the circuit designer can review his design. Okay, so the fault detection can help in identifying redundancies in the circuit. Okay, so that is one. Okay, now there is okay, another term which is known as fault coverage. Okay, so you have this right complete detection test set, means a test of set of tests that detects all the faults. Okay, the quality of test set is measured by fault coverage. Okay, so generally 100% of fault coverage we may or may not do, right? Even if we do cover this many faults, it is typically good enough, right? So we will see this aspect like I explained earlier. Once we have the full fault list, okay, we generally run an random run an algorithm, try to find which are easy, which are difficult. Okay, so if the easy ones actually when we run the random test generation pattern, okay, this will run much quickly, right? Because you are giving random tests and then trying to cover many faults, whereas after for the difficult ones, you have to take each fault and try to do all this justification and sensitization, justification and propagation, all those things you have to do. So it is a time consuming process. So in the random test generation, if you are covering 95 to 99%, you may want to skip some of them also, some of the faults also. Okay, to save time. So time is an essential element. Okay, now that depends on the yield also, right? If you have a proper yield, then like we learnt in the very first class, that total right, faults what is permitted, it is a function of yield and fault coverage, right? So in case you have very good yield, which the manufacturer is claiming my yield is very high, then probably all the difficult faults, okay, you may want to skip, because you are sure the yield is good, right? So this comes from that. So that two formulas which we studied for calculating the faults using yield and the fault coverage. Okay, right? One binomial distribution, if you remember, two models, Agarwal model, we stated those two models. Okay. Now coming to, let's talk about the question which was asked, why some faults were missing in that circuit. So that is because we have something known as fault equivalence. Okay. Now what is the definition of the fault equivalence? Two faults of a Boolean circuit are called equivalent if and only if they transform the circuit such that the two faulty circuits have identical outputs and identical output functions, right? Equivalent faults are also indistinguishable and they have exactly same tests of test. That means, right, if there is a fault here and if there is a fault here, for all the test vectors of that particular fault, if I am getting the same kind of output, similarly if there is a fault here and for the same on all the test vectors, if it is very similar, right, exactly, if it is matching the outputs, then there is no point testing this and testing that. Now you can club that. So now let's take a case of an AND gate. Okay, so 0 0 is good, 0 1 is 0, this is good, 1 0 is 0, this is 1 1. So this is the expected good result. Now if A is stuck at 0, so all the outputs will be 0. So this is the final test vector 1 1, which will identify A stuck at 0, right? So if B is stuck at 0, here if B is stuck at 0 also, all the outputs will be 0 for all the 4 combinations, because this is permanently stuck at 0. So if C is also stuck at 0, all of them are stuck at zeros, right? So if you see the net effect of a 0 fault in an AND gate at any of these 3 locations is the same, correct?
Sir, what about the A slash 0 third row? That should be 1. As in A is,
No, A
that
is
should
stuck at
also
0,
be,
right?
but the good input is 1, right?
No, 0, right? 1 0 is 0, right? AND gate, right? This
But
is
we missed, okay.
It will be 0 only.
AND gate, right?
Okay. No, so but we're checking the value at A or C. At A, when you're saying A is stuck at 0,
No. Output is C always,
okay. Or we're checking at C only. Okay.
right? Output is C,
Okay.
right? This is an output of an AND gate.
Okay.
Okay. So, does it make any sense trying to do these 3 tests, or can we do just one? We can leave aside 2 tests and just to do C stuck at 0. That would be good enough. Correct? Agree, Rahul?
Sir.
Right, so we can just ignore this A is equal to 0 and B. So we say A stuck at 0, B stuck at 0 and C stuck at 0 are equivalent faults. Okay, that is the definition, right? Now if I take the rest of the things, A is stuck at 0, A is stuck at 1. So I give 0 1, right? The output will be 0. So this is 0, doesn't matter. So if I give 0 1, output is 0, but since A is stuck at 1, I will get an output as 1, right? So this is 1, and for 1 0, I get an output as 0 here. If A is stuck at 1 also, since I am giving an input at B 0, this is coming 1, this is 1 1, so this is 1, right? So if I compare this A1 with the good one, the only difference is here. So 0 1 is a test vector which will be required to test A stuck at 1. Okay, so this is a required test vector. Similarly for C is stuck at 1, okay, this is permanently the output is stuck at 1. So irrespective of what you give in the input, all are 1, right? And similarly if B is stuck at 1, right? So for 1 0, I will get a 1 here, which is a faulty output, right? So now from here, if you see here, this test vector is required, right? Because this is unique, right? This test vector is also required. So this is the second test which is required. And now this final test, the bottom one, will clear. So finally, all these tests have to be. So these 3, okay, have come from here, right? So this this one has been catered from here, and from here this one has to be captured, right? Now no point taking this, because when I am checking for this, this is also getting no. So this is a different algorithm to detect, okay, whether these two things that we'll discuss later. As of now, our focus is on this, right? So these are equivalent faults, right? So a single test vector will find. So we'll remove these faults from here and just reflect at the output. Okay, so this is known as fault equivalence. Now, if I go to an OR gate, okay. Now, if you see here in the OR gate, if this is stuck at 1, right, the output will be 1, irrespective of what you give here, right. Similarly, if there is a stuck at 1 at here, irrespective of what you give here, it will be 1 here. And similarly, if I give a stuck at 1 at the, if there is a stuck at fault at the output, irrespective of the input combinations, it will be 1. So if you see here, right, if there is A stuck at 1, B stuck at 1, or C stuck at 1, the outputs will all be 1 here, right? So whereas if I have to detect these faults, okay, I have to put a 0 here, right? And the only way I can put a 0 here is this, the condition, this particular condition, 0 0 0, right? And then output should be 0. So now only for this particular first condition, the output is in variance with the input which is given here, right? So these three stuck at 1 faults for an OR gate, okay, they are equivalent. Okay, we say they are equivalent. Okay, for stuck at 0, stuck at 0 faults, okay, there are different test vectors are required. They are not equivalent if you see here, right? So while for an AND gate, okay, all stuck at zeros are equivalent. For an OR gate, all stuck at 1 are equivalent. Is it okay till here? Yeah.
So
Yes,
just
sir.
Yeah.
There is one doubt. So even for the at this slide, if we say that like the last three vectors, we just need to check at C, right? Because if the fault is C or B, doesn't matter, right? So no need to check. Only C and 0 needs to be checked, right? If we take the condition for stuck at 0, we need to check the last three vectors, because even if B or C has a fault, it doesn't matter, right? So just checking with C at 0 should be enough. Just a
About
doubt.
you're talking about these vectors?
Yes.
No, these vectors. See,
No, actually,
if you're talking about these vectors, okay, these three red are faults, okay, with respect to the good. So you have to give this first vector, because this is an they are fault equivalent, so they get covered, right?
Okay.
But B stuck at
has
0, you have to give this particular test vector, right, in which C also gets covered. Then you have to give this test vector, because A stuck at 0 is identified only by this test vector. So this is mandatory and this is mandatory. This you could avoid, because this is already covered in this test. So 3 test vectors will be required to cover all the faults.
So my question is like, is it if we already have one gate that's faulty, do we need to check for? If we already know that C0 is getting detected, do we need to check for B at 0? Is also what I'm asking.
No. Okay, that is no, that we will learn when I do the random test pattern generation. Okay, so I take this for faults. Okay, there are 1 to 10,000 faults. Okay, so for first test pattern I will run. Okay, and the moment I encounter a fault, okay, I will suspend the run.
Okay.
Okay, then I will move to the next gate.
Okay. Understood.
Right?
Understood.
Or generally it's not done for a gate. Okay, the test pattern will be done for a small module. Okay, which can have say 50 gates. Okay, now I am running a test pattern. Okay, the very instance I get the first fault, I will suspend my test run and say okay, there is a fault here. Okay.
Understood.
Right,
Thank you.
but if I have a time or this thing, and I can probably run the entire thing. Okay, only then it would if I run, I can do that, suspend the fault, or if I it is not actually, the fault is not suspended, right? If the entire fault is covered, then it is suspended. Otherwise, it will try and run the entire scheme so that the data is available for the fab engineer. Okay, where all the finally, if we just detect the fault and say it's not functioning, it is better to run the and say which are the faults which are there, which have been detected. So the test pattern would run the entire thing. Okay.
One more thing,
Yes.
sir. Like actually, the output is independent of A and B if it's getting stuck at 0 or at 1. So if even if you're changing the value A and B, in output is stuck at 0. So how are we gonna test that? It's basically in the pattern that you showed 3 values, that even if A is stuck, we are getting output as a result to identify whether A is stuck or not. And even B is stuck, we get an output to see whether value of A, B, or A, any of these values are stuck. To get the result is showing us whether the value is getting stuck or not. But if the result itself is stuck, like 0, suppose the is in your chart you mentioned result C is stuck, then if C is stuck at 0, all the values will be 0 no matter what. And if it's stuck at 1, all the value will be 1 no matter what the previous values are.
Yes.
So to identify like those scenarios in which the output is already stuck.
No. If the for us as of now it is good enough if we have detected whether this output is stuck at 0 or 1, right? Now because we will do a fault collapsing, right, and try to detect whether there is a fault with a gate or not. Okay, this is my first run, right? And subsequently, if I have to once I have identified that okay, this gate is faulty, and then I want to give more information to the fab lab engineer that okay, so that I have to say in particular is the input stuck or output stuck. I might want to run more detailed fault analysis. But when we are speaking in terms of say 10,000 gates or say 1 lakh gates circuit, right? It makes sense to collapse these faults. Otherwise, it is going to take a lot of time, right? So, and we are going to assume that, right? There, the yield is good, and there is very less probability of faults. So, we might first our assumption is there won't be any faults, right? So, we go by that logic and try to collapse these faults, and we are not by collapsing we are not neglecting anything. Okay, we are covering those faults, right? Because when I am doing this particular fault, I am covering these faults also, because if this fault is there and this is not there, still that is being detected. So I'll run that, and I am trying to minimize my fault list and save time. And once I identify the fault, then probably only for that particular gate I can give additional test vectors and try to further analyze the fault, right? So that is the logic. Is it okay, Aditya?
Yes.
Yeah.
One thing. So if the vector A or vector B, the input vectors are for getting stuck somewhere, so will that be a problem of gate, or will that be a problem of the input units?
No, it could be anything, right? Here, when we talk about a fault, okay, many the defect could be anything, right? The defect could be there is a short from the VDD line, or from the line, or it could be from the previous stage. So we are not bothered very much about how that fault has occurred. Okay. So that is known as we are not worried about the source of defect. We are only worried about the fault aspect here. Okay.
Okay.
Now,
sir, one more question here.
Yeah.
So for big designs which have like millions of gate, how do we decide what will be the test points, and how do we break it down? So does the tool does it, or does the
tool does
designer
it.
put in those?
No, the tool does it, and those are the algorithms which we are going to learn in this course. Okay.
Okay.
This the entire course is about that only. Right.
Okay, sir.
Right. How does the tool does this? This is what we are going to learn in this course. Right. Similarly, for an for now, if you see here, right, now we know this theory, right? So wherever there is an OR gate, right? So the tool will check for stuck at 0, and stuck at 0 here. That's all. Correct? No, stuck at yeah, and stuck at 1 here. So the tool will check for 4. It will generate 4 faults, 1, 2, 3, 4. Because now we are telling the tool, okay, these stuck at zeros are equivalent here. So for each kind of gate, okay, since we know the theory, we are going to tell the tool, okay, so the tool generates the fault list, right? So the tool will collapse these stuck at ones. It will collapse as stuck at 1 at the output. Right. Similarly, these stuck at 0 will be collapsed as stuck at 0 at the output. So the tool will minimize the number of. So the tool is going to generate the fault list for us, and it will do the optimization based on the theory which we have discussed. Right. Similarly, for a NAND gate. Now, if you see here, for a NAND gate, if I give if output is stuck at 1, obviously all of them will be 1. If the output is stuck at 0, all of them will be 0 out here. Now, if A is stuck at 0 or B is stuck at 0, right? So I'll have this output as 1, 1, all are 1 here, and if C is stuck at 1 here, then also I have all ones here. So if you see here, these faults are equivalent. A stuck at 0, B stuck at 0. For an AND gate, the output stuck at 0. But for a NAND gate, it is 0, 0 and 1. So if you see from this table, okay, this is the test vector which I need to give. 1, 1. The expected output is 0, right? But if you either have A stuck at 0, obviously it is not an AND, so I will get a 1 here, because I am giving 1, 1. So expected output is 0. So if either of the inputs is stuck at 0, I will get a 1, which tells, okay, which is a deviation from the good output, right? So this 1, 1, and similarly, if the output itself is stuck at 0, is stuck at 1, then also I'll get 1. Again, that is a deviation from the good signal. So these 0, 0 and 1, they are equivalent. So I can collapse this. So in fact, I can remove these stuck at zeros from here, and I can just keep this stuck at 1 here. Right. So finally, I will have a stuck at 1 fault here, stuck at 1 fault here, stuck at 0 fault here, and stuck at 1 fault here. So from the 6 stuck at faults, I will finally have only 4 of them actually. So that is good enough to cover all the 6. Is this okay with all of you till here? Yeah, Gokhale, okay?
Yeah, C stuck at 0, a fault there. The red one for the C stuck at 0.
Yes, we are not talking about that now. We'll talk about that later. Okay. Okay. As of now, what the software will do is, right, that whether that is also getting detected or not, that's a different issue. As of now, right, this thing, because if you see here, these are here, this is a good signal, right? This is supposed to be 1. I am getting a 0 here, right? So there is a variation. So these faults are equivalent. I am trying to find equivalent faults. Equivalent fault, the definition of the equivalent fault is, right, these also, like you said, this fault is going to detect this also. So that also we will see how to now go about minimizing that. In the first step, what we are going to do is fault equivalence. Fault equivalence means this. If you see here, for all the 4 input possible combinations, the good one, right, and the outputs corresponding to these faults, they have to be exactly match. All these 3 columns should exactly be matching, and where the fault is getting detected, and that also has to be matching, exactly matching. So only for that we call it as fault equivalence. These are not equivalent faults, although for this test vector this fault is also getting detected, right? But it is not an equivalent fault. Okay.
Sir, for C
Sir,
stuck at 0, vector should be 0, 0, right? Not 1, 1.
For yes, that's it. Yeah, for C stuck at 0, this is a good signal, and this is a 0 signal. So obviously the test vector required to detect yeah,
I think, sir, the
I think
color
it's a
coding is
color
wrong
code.
for
Okay.
this.
Yeah.
Let me change that, otherwise I'll find it. Okay. Yeah, I think now it's fine, right?
Even for 0, 1 and 1, 0, it needs to be changed.
Okay, there's some other errors also. For
Input 0, 1 also. C stuck at 0 should be error. And even the same for 1, 0.
yeah. Okay. So for the NAND gates, these are the faults which can be collapsed. Yeah.
So the collapsing will be with respect to output only.
Yeah, we'll
Generally, we are
these two inputs. You can actually collapse it to one of the nodes. Generally, the equivalence fault collapsing, we'll put it into the output. We'll move it from the input and put it at the output. That's what the algorithm does. Okay. You can retain any one of them. Doesn't matter. Okay. Similarly, for an NOT gate, a stuck at 0 is equivalent to stuck at 1 at the output, and a stuck at 0 at the output is equivalent to stuck at 1 at the input. Okay, so they are equivalent fault. So this is again for the NOR. I have not made a table, but you can for an AND gate. Okay, if I summarize, for an AND gate, 0, 0 and 0 are equivalent. For an OR gate, 1, 1 and 1 are equivalent. For a NAND gate, 0, 0 and 1 are equivalent, and for a NOR gate, 1, 1 and 0 are equivalent. Okay, and for a NOT gate, 0 and 1 and 1 and 0 are equivalent. Okay, and if there is a simple line, okay, then it just gets reflected as it is. Okay, so this is the thing which we need to remember. Okay. Obviously in the exam there is no tool, you have to do it yourself. So I guess these things you should remember. Otherwise, because in exams we are going to give small circuits and you are expected to do these analysis. So you need to remember these fault equivalents, right? Okay. So now the thing is, this is how the software would do, right? The stuck at 0 from here to here is removed and put here. So the stuck at 1 faults here is removed, and this is retained here. Okay, it is not kept. This one is retained. Okay, this 0 is retained. So at the outputs it is retained. Now if you see, to start with, if it is an n input gates, okay, initially we had 2n plus 2 faults. Okay. 2n for the faults at the input and 2 fault at the output. Okay, so total 2n plus 2. Now this 2n becomes just n, so n plus 2. So because of fault collapsing, from 2n plus 2 we just come to n plus 2. So these are the faults, how after fault collapsing these gates look like, right? So how does it help? Reduce the number of faults so that it speeds up the automatic test pattern generation, and it will shorten the test set. Okay, so that is from 6 for a 2 input gate, it would come to just 4 for a 2 input gate. Similarly for any n input gate, so this is the formula which is given. So there would be saving in time and effort. Okay, so that is known as equivalence fault. Now if I take this particular circuit, what the algorithm does is, it will put the fault at the output first. It will start from the output and then it will start moving towards the input. So here the output, it will put an 1. This is an NOR gate. Now if I have to look at the NOR gate out here, right? In the NOR gate, okay, the stuck at 1 inputs are taken care of at the output itself. So there is no stuck at 1. So I put only stuck at 0 faults here, right? Then I come to the NAND gate here. Now if I take the NAND gate here, only the stuck at 1 faults, here the stuck at 0 fault, right, is available. The stuck at 1 fault has already been taken care of the next gate. So stuck at 0 is there, and for this NAND gate, the stuck at 0, this stuck at 0 takes care of the stuck at zeros here. So I just have to put stuck at 1 out here, right? Now for this particular OR gate, the stuck at 1 has been taken care of by this stuck at 1 here. So I have to put the stuck at 0. So if you see here now, by running this algorithm, right, now I have 1, 2, 3, 4, 5, 6, 7, 8 faults. Whereas if I count the number of nets, 1, 2, 3, 4, 5, 6, 7, 14. So you can see that from 14, okay, by running EFC. EFC stands for equivalence fault collapsing. I have reduced my total number of fault sites, okay, the fault list to 8. Okay, so is this logic understood by all of you? How to move from the output and come towards the from the primary output you come to the primary input. So these are the faults which will be there once you run this algorithm on any circuit. Is it okay with all of you?
Okay.
Okay, so let's move forward. So this is another example which I have put. So here it is stuck at 0 and stuck at 1, right? I start with, and for an OR gate, okay, there is a stuck at 1 here, stuck at 1. First I write all the whatever is the faults here. Now this stuck at 1 I have cancelled it. Okay, if you see, it is highlighted. That means they have been moved here, so I don't have to worry about that. This is stuck at 0 here. This is an AND gate. So this stuck at 0 and this stuck at 0 had been removed here, because this stuck at 0 will take care of that. So I have removed that. Here also there is a stuck at 0, so I'll remove this and I will remove this. Right? So that is how okay, so this is how I can so from 18 faults I have come down to 12 faults. Okay, so this is how I can reduce the faults, okay, number of faults by running this equivalent faults collapsing. Right now, if there is an like we learned in the tell me.
So in the previous slide, at the output of the NOT gate, so let us say if we consider any one of the NOT gate, if the output is stuck at 1, shouldn't it be equivalent to input is stuck at 0?
If the output is this stuck at 0 has been shifted here, right?
Yes. No, but for the NOT gate, there is stuck at 1 also at A2 pin, right?
Actually, at A, this is coming here, right? So there could be a stuck at 1 here also, right? So if we eliminate this, okay, so because there is a branch here, we don't do that.
Okay, so whenever the branching is there, so we will have to consider both the cases.
Yes, both the branches. Okay. That is what is explained here also, right? If there is a branch here like this, right? If there is a branch here, all the faults will not be equivalent, right? So if I make the same table which I made here, so if you see here, E stuck at 0 is not really equivalent to L stuck at 0, because now it is branching. Whereas in this path, since there is only an inverter, it doesn't make any difference. So E and F are equivalent. Like this, E and F faults are equivalent, but E and L are not equivalent here like this, right? So that is the reason whenever there is a branching thing like this, okay, we will not collapse, right? We will not do a fault equivalence directly. Right, so we will assume that this is a separate module and this is a separate module. and then we don't push this this fault here or this fault there, okay, while doing the fault collapsing. Okay, so whenever there is an branching, right? So but if there is an inverter like this and direct input is given, then these can be equivalent. Okay, but if it is going to some other gate like this through this branch like this, right, then they may not be equivalent. Okay, so that is what is for the branching, right? Yeah. Now we talked about fault collapsing. Like for an AND gate, you have a 0 here, 0 here, 0 here. You can represent it at any one place, that is good enough. But the algorithm generally puts it at the output node. Okay. Now there is something else which is we are going to learn, which is known as dominance fault collapsing. Okay. That was equivalence fault collapsing, and now we are talking about dominance. Now suppose there is an stuck at 1 out here, right? So the only test vector, okay, to detect a stuck at 1 here, you can give any 3 outputs. Okay, I have to get a 0 here, so I give 0 0 0 1 1 0. Any of these test vectors, 3 test vectors, will detect a fault f2 stuck at 1, right? Suppose I have a stuck at 1 here. Okay, now if this is stuck at 1, right, so the only test vector which will detect stuck at 1 out here will be 0 1, right? I have to give a 0 here. Okay, and still if I am getting an 1 here, that means there is, so this, now this 0 1 is part of this, right? 0 1 is here, 0 1 is here, so I say f2 is dominating f1. Okay, that means this fault, okay, is an as far as the test vector is concerned, this is subset of this. So which fault we should actually try and find, f2 or f1?
F2.
Why f2? If I find out f1, right, because there is only one test vector, right? So here f2 dominates f1, okay, but which is dominating, I remove that. Okay, if I find this stuck at 1, okay, I am giving 0 1 test vector, obviously this is also covered by that. Okay, so if f2 is dominating f1, then I can remove f2. Is it okay?
That's a one point. Stuck at 1 at f2, it can also detect stuck at 1 at the other input of the AND gate.
Here, right? Yeah.
Yes.
So you are right. Okay. So f2.
Yes, that is what, right, we did in the last example, sir, right?
Yeah. No. f2 can be brought here, right? Or if I write here as f3 stuck at 1, right? This can be brought here. Okay, and vice versa. But these are not equivalent. Okay, these are not here, right? So these are not they are not equivalent. Okay, so this can be brought here, this can be brought here, but this stuck at 1 and this stuck at 1, their different test vectors are required. Is it okay?
Yes, correct. Got
right?
it.
So that is the difference between equivalence. In the equivalence, right, the definition of equivalence is all the 3 faults, like for stuck at 0, for all the input combinations, the output characteristics will be the same. But here that is not the case. Okay, so once we take a table, it would be clear. So this is the table, right? Now if you see A stuck at 1, and B stuck at 1 and C stuck at 1. So A stuck at 1 has got a different test vector, B stuck at 1 has got a different test vector, but C stuck at 1, right, is covered by A stuck at 1, and C stuck at 1 is also covered by B stuck at 1. Okay, so if you see here, right, so this is a single arrow which is shown here. That means from here I can move it here, from here I can move it here, right? But for stuck at 0, I am showing a double-ended arrow out here, that all 3 are equivalent. I can place it anywhere, doesn't matter. Okay, so finally, is this a good option? I keep 2 here and 1 here, 2 stuck at 1 here and 1 stuck at 0 at the output. Is this a good option?
Yes, sir.
For a AND gate. Okay, okay. So what the algorithm first does is, okay, it will just keep moving everything to the primary inputs if there are many gates. Okay, so stuck at 1 here, stuck at 1 here, stuck at 1 here, and stuck at 0 here for a 3 input AND gate. So these are the only 4 vectors which is good enough to check this gate. Are you all agreement with this? For a AND gate, if I do this testing, will it detect 1, 2, 3, 4? 4 into 2, 8. So instead of 8, I just have these 4 test vectors. Is it good enough? Or your agreement? Because this stuck at 1 is brought here, stuck at 1 brought here, stuck at 1 here. Stuck at 0 are all equivalent. So I can put it anywhere. So in this case, I'm putting it here. Right? Time being. Okay. So
why do we need the last stuck at 0 false?
Sami,
The
क्या कर रहे हो?
the last one SA0.
Pardon?
Why do we need so for a 3 input AND gate, the first 3 stuck at 1 and so the last stuck at 0, why do we need? It should be at the output.
That's it. It can be it can be anywhere. It can be here, 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 or here.
Okay.
Right?
Understood.
1 stuck at 0. Okay. So this is so for a gate like this. Okay, from here to here I can move. From here to here I can move. Similarly, here to here, these are equivalents. Okay, so this is the kind of shifting which is possible. So if I'll take an example with that, things will be clear, right? For that we talked about the AND gate. Similarly, for an OR gate, okay, for an OR gate, so these are stuck at zeros, right? So if I write for the stuck of 0, if you see here, if A is stuck at 0, right? So this is the for where is it? A stuck at 0, right? So 101 is the test vector which will identify that, right? And for B stuck at 0, 01 is the test vector which is required. For A stuck at 0, 10 is the test vector, right? And if the output is stuck at 0, right, here, right? So this either of these test vectors is good enough, right? So I can when I'm so I can say that this is C stuck at 0 is dominating A stuck at 0 and B stuck at 0. It is dominating these two. So what I can do is here this stuck at 0, I can either move it to here, and or I can move it to here, or I retain this, I can remove this if I am having it stuck at 0. Similar to so finally the OR gate looks like this. Okay, there will be a stuck at 1 here, and there will be stuck at 0 and stuck at 0 here. Like for a NAND gate, what we did, we had it stuck at 1 here and stuck at 0 at the output. For an OR gate, it is the other way around. Stuck at 0s will retain here, and then stuck at 1 at the output we will retain. So again, from the 6 faults, now we have finally zeroed down to only 3 faults. Okay, so this is known as a dominance fault. So if I go to a NAND gate, similarly, if I make a table for this, and if you try to analyze these things, okay, it will be, I'll share this PDF with you. You can do this analysis. So finally we see this is what you need to remember. So for an AND gate, on these 3 tests will be good enough. Stuck at 1 here, stuck at 1 here, stuck at 0, right? Because these stuck at 0s equivalence is here, right? And for stuck at 1 here, it is, these are dominating. So this has come here, right? So similarly here, so red indicates an dominating. Okay, so for a NAND gate, if you see here, stuck at 1, stuck at 1, and stuck at 1, you don't have to bother about stuck at 0 anywhere, right? So that will be covered, right? So by that, similarly for an OR gate, stuck at 0, stuck at 0, and stuck at 1. So this is they are complementary, right? And gets replaced by the OR gate. For an NOR gate, it is all stuck at zeros. For a NAND gate, it is all stuck at ones. So for these 4 gates, which are generally used in a circuit, these are the test vectors with this DFC rule. Okay, when we are using EFC algorithm, then there will be 4 test vectors. when we are doing dominance fault, there is only 3 test vectors. So one more test vector is removed here. Okay, this is by further refining the short list. So this is what is known as dominance fault collapsing. Right. So what it is done here, what the algorithm does is, first all the faults are there, right, and from here, okay, it is moved towards the input. Okay, it is moving towards the input. So as you move, it is shown. So finally you have everything in the input. Okay, once you have everything in the input, okay, then these two red, can it be moved as a single at the output? No. But can the blue can be moved here? Blue is stuck at 0. Can it be moved here?
Yes, sir.
Yeah, because that is equivalence, right? So first a DFC run will run and bring all the faults to the primary inputs. Once it is brought to the primary inputs, using EFC, only from the primary, one will be further optimized. So from here, if I come here, okay, further, so these are 2 blues will come here. Okay, it is only done for the primary inputs. Okay, so there are this is removed from here. So okay, and similarly this is removed here and it's put here. So this is how the DFC would run. Okay, so originally there were 18 faults. If you run the EFC, you will get 10 faults, and if you run the DFC, you get 7 faults. Okay, so this is a finer refinement of the earlier thing. So you got to remember this. In the DFC, what it is done is, from the output, everything will be pulled towards the input side, and then and the final, after when we have the input, one equivalence run at the primary input is done. So further. So that is how. Now if you see here, this is EFC for the same gate which we discussed, right? Now if I see the DFC, if I run the DFC, now this E0 for a NAND gate is not really required. So you can further reduce it to these many faults. So you can refer to this table, right? And then you see that in the DFC, the number of faults further. Everything is brought to the primary input from here to here. So please do this yourself once, because in the exam you might get a similar pattern questions. And then from the primary, okay, this is an OR gate, so C1 is shifted here, right? So this is how it is done. So just verify this circuit, and in case you have any doubts, we'll discuss about it. So this is known as DFC, right? So these are the 2. So similarly, if there is a branching operation, then these have to be considered as separate. Okay, so you can't collapse that. So that is one option what we have. Now if you see, there is the third algorithm is checkpoint theorem. Okay, the checkpoint theorem says at all the primary inputs, okay, these are all primary inputs 1, 2, 3, 4, and at all branches, okay, you put all the stuck at faults, like stuck at 0 here, stuck at 1 here, stuck at 0, stuck at 1, stuck at 0, stuck at 1, stuck at 0 here, 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 here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So total fault sites is checkpoints are 10, right? So you put all the faults at these sites. Okay, it says if you put all the faults at these sides, then it is good enough for checking the all. It does the entire fault checking. Okay, it says. Okay, so if you do, that is what the checkpoint theorem says. Okay, if you have a fault side, if you put the faults at these nodes, okay, it is good enough. Okay, so
excuse me, sir. I'm sorry to interrupt you. Sir, I'm sorry to interrupt you, but I don't know if it was my problem or your mic issue. There was a little bit fumble in between your explanation, so I didn't really get what you said about the theorem. Can you please explain it? Thank you.
Sure. So the checkpoint theorem says at all the primary inputs, okay, and at the branching, at all the branch, if you do, okay, then it will cover all the faults. It is good enough. So there is here, if you see here, this is not a primary input, nor is it a branch. This is also a wire net out here. So you don't have to check for these points, it says. If you check only at these points, it is good enough, it says. Is it okay?
Okay, sir. Thank you.
Right. So that is what it says. Ki, okay.
Oh.
So it says ki, okay, if you do
But
this,
sir, just one question. Yeah, as per this theorem, that in case of there is any branching or is there any primary input, only those points we have to check.
Yes. Yes.
But at the same point, if there is output, it'll get stuck from the gate one. Suppose I'll take the example from the gate one.
Here.
If the output of yes here. If the output gets stuck here, then how are we gonna check that?
No, it says ki, if you do this, this will be this will take care of that. Right? That if you see the fault equivalence will take care of that, or fault dominance, it will cover. One of them will cover.
Basically, so it will cover this test will cover the particular scenario only.
Yes.
Oh, okay. Thank you.
Right. Okay. So there is so it will so there now we have learned about the three techniques. Okay, now if I cover the three techniques, okay, if I do the checkpoint, okay, for example, if I the same standard circuit, right, originally there were 18 faults. If I run EFC, it was 10 faults, right? If I do DFC, it will be 7 faults. But if I use the checkpoint theorem, okay, there will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? There will be 10 faults. Generally, okay, checkpoint will give you more number of faults. Okay, so this one is the will give me the least number of faults. Okay, it will optimize it better. Then followed by this, followed by this. Okay. But then why do we generally what is the disadvantage in moving from here to here or here to here is that now you are talking about only about, we are only taking examples of 4 gate. When I talk of millions of gate, the algorithm DFC takes lot of time. Okay, EFC will take lesser amount of time, checkpoint will take even lesser amount of time. Okay, to run minimize the total fault list. Okay, now it is time versus total list. Okay, so if you can afford a large amount of time, then you can run a DFC, right? But if you don't have that much of time to list your entire faults, then you can go for checkpoint. Okay, so generally EFC is done. This is a simple algorithm. This is a complex algorithm, right? Like for explaining purpose, we are saying, okay, we move like this, move there. But implementing it in a software algorithm, it is slightly complex. Whereas an equivalence is nothing, okay, right? So it is fairly easy to implement. Okay, so that is the reason why generally we go for EFC rather than checkpoint is the easiest one to implement. Okay, you just run the netlist. From the netlist, you give all the faults at the primary inputs, and wherever there is branching on those netlist, you give again all the faults. Simple. So it will just take a few minutes or something like that for even for a very big circuit or with a few thousand transistors within few minutes or maybe 1 odd hour. This will give me the entire fault list. Okay, this is the simplest algorithm. EFC will take slightly more, maybe it may take 10 hours, 12 hours to generate the fault list. DFC will take maybe 3 days, 4 days kind of to run the algorithm, but the final result which will get by if you are able to spend that much time is that the total fault list will be lesser. Okay, that might help in the next algorithm. So if you have reduced the number of fault lists, the next algorithm, it could be helpful. Okay, next algorithm is what? After finding the fault, you have to generate the kind of test vectors, right, for that. So this is what, these are the 3 algorithms. Okay, now this is another, okay, checkpoint is a simpler alternative to EFC, DFC. Okay, DFC has issues also in sequential circuits. Okay, when we learn about sequential circuits, it is has got implementation is slightly difficult, that algorithm, but EFC is the most preferred technique. Okay, so that is this is just a collapse ratio. Total number of faults is this, right? After collapsing, these many faults are there. So not all faults, when you run a particular algorithm to detect the faults, not all faults will be detectable, right? So various algorithms will have different detecting capacity. So it depends on what algorithm we are going to choose. So we'll learn those algorithms later on. So suppose these are which are untestable faults. You can't do the test, right? So when you run an algorithm, it will say, okay, these many faults have been left out. Now whether I want to cover that those left out ones, I can go for specific runs, another runs, that each fault I can find the test. So that option is also available, and those algorithms also we are going to learn. But whether I want to take a decision of leaving that right and moving ahead, that depends on, if I don't have that, that depends on the yield, okay, and my final what is the fault coverage which is desired. So this is the fault coverages, okay. So that decision we have to take later on, right? So that is how. Now in the next class, right, we will I'll talk about design verification, okay. Although testing is what testing is actually trying to find out if there is a fault or not in the circuit, okay. In testing I am not really checking the logic verification aspect, okay. So logic verification aspect will be done here, simulation for design verification, okay. After that, after the fabrication, the testing is essentially trying to find out faults which might have occurred during fabrication. Testing is not focusing on logic verification, okay. It is only right, I am not trying to find out if a plus b is giving c or not in testing. That will be done in design verification, right? In testing I am saying that, has this OR gate implemented properly, right? Is there any fault in this particular circuit, okay? That is a fault. But to do that, right, for doing the testing, right, I should have, right, what is expected. If a plus b, if I am giving some test vectors here, what is the correct output which is required? And then if I give some test vector and for a particular test vector, if there is a fault, okay, then there will be variation, right? So this logic verification also becomes part of testing, right? True value simulator, because we have to know if we give a particular test input, although in the testing we are only focusing on fabrication issues, but the logic also plays a role in the testing, because unless we know what is the expected correct output, how can I do a testing? I can't do, right? So logic verification also becomes a part of the testing, okay, some part of the testing, and hence because we have to generate the correct bit. So this is the block diagram. So you have an specifications from which you will synthesize and you will get the netlist, right? And in the netlist you run a true value simulator, right? You given from the input itself, you given true value simulator is nothing but logic verification, proper logic verification, okay. I'm giving a set of inputs and giving a set of specific inputs and checking for the output. This is nothing to do with faults and defects, okay. True value means I am adding and I am doing an OR operation and 0 and 1, whether I am getting output 1 or not. That is the verification here. So that needs to be done here. And now you can't have an exhaustive true value simulator, right? You have to check for a set of like which are in the critical path. Otherwise, like we said, there is a lot of scope here to minimize the number of true value simulations, okay. Now this table is also equally important for our fault simulation, because without this we can't move ahead. So this run has to be done. So this is known as simulation for design verification. So if there are any between the when we give the true value simulation and computed results and we do the analysis, if the result is not expected as per expectations, then we need to change the design. So this run before we start generating the test run, so this information should be available. So this, because this the true value right simulator values are required for the test pattern generation, okay. So that is there. So, but then we may not do an exhaustive testing. Okay, so some examples I will discuss in the next class, where how can we minimize this. Okay, so now the problem out here is here that the number of test vectors which are given for an true value simulation is not fully automized. Okay, so it depends, because if you try to do fully automized one, then it can't actually the simulator cannot actually, there's no algorithm really because it is very specific to circuit, okay, whereas the faults and all, it is universal. Okay, for a AND gate, okay, these are the faults, these are the fault equivalents, these are the dominant faults. But for logic verification, okay, some circuit which is made by Jaysingh may not be exactly the same as Ranjani, right? So it is very specific to circuit, and hence there is a lot of human intervention involved there in minimizing the test vectors. Okay, so that is one of the weakness, and hence the best engineers are generally put in formal verification, where during true value simulation we try to minimize the test vectors. Okay, so okay, so this is just an example out here. We are talking about true value simulation now, right? I have an 32-bit adder, full adder, right? Carry, look ahead, ripple carry adder. This carry is taken here, this carry is taken here, this carry is taken here, right? So how many for logic verification, how many test vectors are required? Can anybody make a guess? For exhaustive checking, I want to check functionality of each of these logic blocks. 100% checking I have to do. How many test vectors will be required?
2 to the power 32.
2 to the power of 32. Yeah, Aditya? Lowest bidder will will get the tender here. Anybody proposing lower than 2 to the power of 32? Yeah, Jaysingh?
No idea, sir.
No idea. Anybody? So this is where the tool cannot optimize. Okay, but it's a modular structure. This is a modular structure. Okay, and one who has designed with his intuition, he can reduce the test vectors, and only 8 test vectors are required. Okay, now if I give 0 0 0 0 0 to all these full adders, right first, so there are total 32 adders. Okay, 0 0 0 is given to all the full adders. Okay, then I give this 0 0 1 this test vector, so 0 0 1 is applied to all the full adders, right? I give 0 0 1, right? This is an internal node. Okay, this is an internal node, so this 0 is already available here. I give 1 1 here, so 0 0 1, then this 0 is available from inside this carry. I give so it is like it will become 0 0 1 here. Again this 0 is available internal 0 1. So have you understood this particular table, all of you? Yeah, Jaysingh?
Yes.
Okay, let me repeat it once. If I give 0 0 0 0 here, what will be the input of all these testers, all the full adders? 0 0 0 0, right? Each full adder has got 3 inputs, right? So what is the maximum input combination? It has 2, right? It has got some outputs. It has got input combinations is 3, right? So if I give all zeros, so first condition. The next condition is I am going to give 0 0 1, right? This 0 is carry from here. So this is 0. My test vector is 1 1 here. So 0 0, no. I have to give 0 0 1, right? So I give 0 here, 1 here. For first I give all 0 0. The second test vector will be 0 0 1, right? This 0 is coming from here, 0 1. This 0 is coming here, right? So it will be 0 1. So this is the second test vector which I can give. Correct? So
Yes, sir.
only 8 test vectors, right? only 8 test vectors are required, right, for this. So we were speaking in terms of 2 to the power of 32. Now we are just saying the 8 test vectors are good enough. Okay. Now this is possible only because this is an modular circuit. Okay. So here if you see no algorithm can pick up these test vectors. It's only the human who is designing these circuits, he can come up with such optimizations. Okay. So that is where the logic simulation is very it is still not automated to that extent. Okay. So we don't have robust algorithms which will come up with such simplified solutions. Okay. So if they are not modular, it becomes even more difficult, and then that's where the role of the designer comes in. Okay. So the test engineer can a job is more or less automation side, whereas the one who has designed this circuit, okay, a circuit design, he can only do the logic verification aspect.
Just one question that I have, like suppose you increase the number of bits, 1 A B C, and it's going up to 31 right now. Okay, the possible combination with from these bits will be I guess it will be infinite. If you increase if you keep increasing number of bits, the combination will be infinite. So how this 8 vectors are like rectifying those combinations? How is going to solve taking 8 vector will solve this combination problem?
No, here I can keep increasing. I can put another full adder. But if you consider this full adder as a module, right, the number of inputs for this particular full adder is only 3.
Okay.
Right, they are actually parallelly. I am doing a check of all these full adders. Right.
Okay, so basically it's kind of running a string in a parallel instead of doing in a series.
Yes.
But the output is connected in a series. No, that's what it's making it complicated. Like C1 is connected as an output of 1.
So you
cannot operate A1, A2 at the same time when you're operating A0, B0, and C0.
Yeah,
it has supposed to be an output of.
Yes. So that's what only that's where the difficulty in automation lies. So you have to know, because this is internet. So for testing this, okay, this 0 is coming from this block. So this is how. So you have to be careful with designing the circuit. Right. That is the challenge in automation of these circuits. Right.
Okay.
Right. So now it says 7 and 8. The first 7 vectors actually cover all the stucket faults. Okay. Now if you see here, the stucket faults, if you see at A, B, C, and sum and carry. Right. So if you see here, these 2 test vectors, they are only 7 are required. First 7 test vectors cover all the stucket faults. Okay. So while going from here, logic verification wise, this will be the test vectors which are required. But if you go for further, try to think it from the stucket faults point of view, here out of these 2, only 1 will be required. Okay. So these are the kind of obviously so such circuits are not automated, but from the designer can do some kind a lot of optimization. Okay. So this is what it is done out here. Now if you see here, you also have to find out if I have to find out the max delay of this circuit. Okay. If I have to find the max delay of this circuit, I have to, it is good enough for me. I don't have to check the delays of each and every path. Okay. The worst case scenario, this carry in is coming here, and I have to see that this carry is getting propagated from here to here and to here to here, and it is coming here, and all the sums are getting. So I have to generate a test vector in which the carry is getting propagated through each of these blocks. Okay. So worst case scenario. So suppose I have given 001 to all the full adders. Okay. 001, 001, 001. Right. and from there the next text vector I am going to from here to here. If I am going to move from here to here, right, I am going to give 0 1 0, right, two test vectors, okay, for timing analysis. So when I do this from here to here, right, you will find that this carry is being the entire chain is getting disrupted from here to here, okay, and similarly from here to here, right, this entire chain is getting activated, right. So 2 followed by 6 or 3 followed by 7, where the carry propagates throughout the chain, right, when from here to here, if I am moving from here to here or from here to here, this carry is being propagated. So this is the timing analysis. So these two vectors, okay, this is the first vector, and now 0 0 1, and applying this test vector, right, after that. So this carry gets propagated, right. So this is will I'll talk this slightly in detail in the next class, but just to give a slight hint of what is to follow, so I am telling this. So these are the kind of things which we are going to learn in the next class. So I'll revisit these true value simulation things. So I've just given some hints for you to think about this. And then I will discuss these in the next class again. So just think about it, why on these two test vectors and these two test vectors is good enough for me to check the delay of this circuit, okay. So I'll give you the full explanation in the next class, but you just think over it, okay. So this we are going to learn, and this is how the final thing works like, right. You have a verified this thing, then you have this formal verification. This aspect we are going to learn in the next class, okay. Verification aspect, now how to do the input stimuli. This is verification. Verification is not testing. So from the verification I generate some test vectors, and then I have from the list I have all the faults, okay. Now the faults will come from here, the test vectors with the correct results will come here, okay. Then I run the fault simulator, because I'll induce each fault, and from this data, these test vectors will have the correct output which is available for each test vectors, and if there is an mismatch, okay, that means, okay, there is an that I'll finalize that particular test vector, so it will come to the test gen, right. And also the fault tester say for one particular test vector, multiple faults are being detected. So there will be some redundant test vectors. So this test compactor will start deleting those test vectors, okay, because two test vectors might be giving the same kind of faults. So that will not be required. So that will start deleting some of the test vectors out here, right, because it's already covered in one. So those faults have been covered. So similarly, the faults and multiple faults will be covered here by running one algorithm. So we start removing the fault from the fault list also. So you keep removing, and finally when the fault coverage is done, we stop the. So this is what the general algorithm looks like. So as of now, till now, we have discussed about faults. We have discussed about faults collapsing, okay. Now we will talk about this aspect in the next class, about the verification aspect. Then we will talk about how to do the various simulation algorithms here, right, to generate the various test vectors, and how to minimize this, okay. We ultimate aim is to make this faster, okay. So don't think in terms of one gate, two gate. If we have millions of transistors and few thousands of gates, so then if you don't have an minimized test set, right, it is going to take time. So it is very, very important to run minimum number of test vectors and cover maximum fault, okay. So this course is all about that, okay. So these two aspects, faults and fault coverage we have covered. We will talk about verification, logic verification. Okay, although this is not purely testing, but this is very, very important for us to move forward. So that is why one class I would love to spend on this aspect. Okay, so in the next class we meet and we will discuss that aspect. Okay, thanks a lot for today.